I want to go over a few concepts of Lewis symbols and Lewis structures to help you prepare for tomorrow's quiz. So with Lewis symbols, we represent the valence electrons, the outer s and p electrons of a given atom. So for example, sodium is in group 1. So we represent that with a single dot, which represents the s electron within sodium. Barium is in group 2, so we can represent that with 2 electrons. Now, you can draw the 2 electrons together. The alternative way would be to draw it like this. I will not count off for either drawing. And antimony, well, antimony is in the same group as nitrogen, group 15. 1, 2, 3, 4. This would be equivalent to group 14, and then 5. The 4 positions represent S, Px, Py, Pz. So S, Px, Py, Pz. So we have 4 valence atomic orbitals, and so we're populating the electrons in them. So these paired electrons, again, would represent putting 2 electrons within an orbital. We don't have 5 orbitals to work with. Again, so 1 electron in group 1, 2 electrons group 2, and then we jump to group 15. Now we have 5 valence electrons. I would recommend getting comfortable just picking elements in groups 1 or 2, 13 through 18, and practice drawing those Lewis symbols. Lewis symbols are the first step to get us to Lewis dot structures. And Lewis structures get us to molecular structure and 3-dimensional structures. So it's very important that you are grounded with Lewis symbols. Always have a periodic table handy when you're doing this. You'll get one on the quiz. As we go from Lewis symbols to structures, we're still looking at the valence electrons, those outer s and p electrons. H3O+, hydronium. So this is the active ingredient in an acid. Why does hydronium have this chemical formula and charge? Well, this is something that we'll find that as we analyze chemical structures, they tend to obey the octet rule for elements in the S and P block parts of the periodic table. So, with hydronium, let's count up our electrons, our valence electrons. So we have 6 from oxygen, we have 3 hydrogens, so that's going to be 3 times 1, 3 electrons. But now we have a charge. This is a polyatomic cation. So for our charge, we remove an electron. So we remove an electron. So this would be 9, now we remove. So we have a total of 8 electrons to work with. Hydrogen can never be the central atom. So oxygen is our central atom. To make this a molecule, there have to be covalent bonds between the atoms. At the very least a single bond, possibly double and triple bonds. 2, 4, 6. So all of the hydrogens are bound together, but we still have 2 electrons left over. So now we've used all our electrons. 2, 4, 6, 8. The oxygen obeys the octet rule. Hydrogen does not have to, so this is the correct Lewis dot symbol, Lewis dot structure. CH4, methane. So this is the first hydrocarbon that you would learn about in organic chemistry. So you have a carbon, 4 hydrogens. Again, Lewis dot structure. First thing, count up your valence electrons. Carbon has 4. We have 4 hydrogens, so that's going to be 4 times 1. So now we have another 4. There's no charge, so we have a total of 8 electrons. Carbon is going to be our central atom. So we just position the hydrogens around it. Again, hydrogen is never the central atom. To make this into a molecule, each hydrogen has to have a covalent bond to the carbon. So 2, 4, 6, 8. We've used all of our electrons. Hydrogen does not obey the octet rule. Carbon has to obey the octet rule. Well, 2, 4, 6, 8. So everything is good. We'll see that the Lewis dot structure does not represent the three-dimensional structure of methane, but that's something we're going to get to a little bit later. But I can't stress it enough. Lewis symbols, Lewis structures are absolutely foundational. They're the cornerstone to getting us into much more complex chemical structures. So if you're having trouble with Lewis structures, it's only going to make it more difficult as we go to three-dimensional structures. So in the case of methane, again, 1, 2, 3, 4 chemical bonds, single bonds. Each line, of course, represents 2 electrons, and carbon is therefore obeying the octet rule. pH3. So now we've got an element that is a little bit lower on the periodic table. You know, we have NH3, which would be ammonia. Well, with phosphorus, even though it's a heavier element, it still has the same number of valence electrons as nitrogen. So for phosphorus, we're going to have 5 electrons. Hydrogen, well, we've got 3 times 1, right? So 3 electrons, because it's pH3. Okay. And so that gives us a total of 8 electrons. Phosphorus is our central atom. Again, hydrogen can never be the central atom. So we have 8 electrons to work with. Well, first things first, we just need to connect all the atoms. 2, 4, 6. Okay, so 3 single bonds. We have 2 electrons left over. We put them on the phosphorus as a lone pair. We've used all of our electrons. Hydrogen, again, does not need to obey the octet rule. Phosphorus, 2, 4, 6, 8. Phosphorus obeys the octet rule, so that is the correct Lewis dot structure of pH3, which would be completely analogous if this was nitrogen to ammonia. So that's one of the great things with Lewis dot structures, is that as you get comfortable drawing them, you'll find lots of repeating patterns, lots of things that you can look at and go, oh, okay, phosphorus is the same as nitrogen from an electron count. We will see that there can be some more complex aspects to chemical bonding for elements like phosphorus, sulfur, and even in heavier atoms, but we'll get to that a little bit later. For carbon monoxide, let's draw its Lewis dot structure and then analyze the formal charges on carbon and oxygen. Carbon has 4 valence electrons. Oxygen has 6. So we have 10 electrons to work with. The first thing is a single bond. What that does is it connects both atoms. We have 8 valence electrons to work with. 2, 4, 6, 8. So 2, 4, 6, 8, 10. We've used all of our electrons. Now, this is not correct. 2, 4, 6, 8. Carbon obeys the octet rule, 2, 4. Oxygen does not. What we'll find, we could go back and forth moving these lone pairs, but what we really need, a double bond, then a triple bond. 2, 4, 6, 8, 10. So we have the same number of electrons, but we've distributed them differently. 2, 4, 6, 8. Carbon obeys the octet rule. 2, 4, 6, 8. Oxygen obeys the octet rule. But now we need to look at formal charge. Okay, so with formal charge, for carbon, carbon brings 4 valence electrons, and it's surrounded by 1, 2, 3, 4, 5. So it's 4 minus 5. So carbon has a -1 formal charge, and oxygen brings in 6 electrons, and it is surrounded by 1, 2, 3, 4, 5. So that is a +1 formal charge. Carbon monoxide is a neutral molecule. However, the carbon has a -1 formal charge, the oxygen has a +1, so they cancel out. You would not know that unless you, again, draw the Lewis dot structure and then analyze it. So, again, Lewis dot structures are very, very important to understanding many aspects of chemistry. And it really starts with, again, drawing these structures and analyzing with something like formal charge, and we'll see other aspects of chemical bonding that we'll analyze using Lewis dot structures.